So we are going to explain ratios that I think more the theory can explain about dark matter, dark energy, and galaxy formation. Actually, what I do gives a candidate explanation for three 90-year-old or more year-old physics problems. One is list all the elementary particles, another is describe dark matter, another is describe dark energy, and we'll get a candidate for all. The approach is probably unique. I just set out to find a math basis that matches the known elementary particles. We extrapolate from there, and eventually you can add motion, but there's a real advantage to not doing that too early. So the basic program is, in one step, we will be able to describe new elementary particles, dark energy forces, and some dark matter. And with one more assumption thrown in, then we can get some more dark matter and explain the ratios that are sort of built for this class. This is a candidate analog to the chart that you see on the wall there for elements, to that periodic table, for elementary particles. So let me explain it. Basically, second column is spin in units of h bar. And if you look at the far right, that's the Higgs boson. 3 charged leptons, so we can action boson. The neutrino winds up in zero mass, and I'll explain why in the next slide that is not unacceptable. The sigma equals -1 particles in today's universe are found only in hadrons and atomic nuclei. And I'll call your attention to the 6 zero mass, zero charge analogs to quarks that fill the box that this theory would get. We'll do the long-range forces on the next slide. They come out with the same math, but they don't display well here. So this completes the periodic table analog in effect, and the math synchronizes the idea that we have no motion in this theory. So if you look for spin 1 mediated long-range forces, there's an interaction that's monopole, that's with charge. There's an interaction with a dipole, that's a nominal magnetic dipole moment. There's an interaction that's quadrupole. Think of the Earth. The axis of rotation of the Earth does not equal the axis for magnetic field. The 2G68 solution that comes out of this will be very important later. For spin 2, we actually get a lot. Monopole of gravity over there on the left. And if you start on the right, those two quadrupole solutions, octupole solutions, are repulsive, and they drove the increase in the rate of expansion of the universe very early on. After a while, as things separated a bit, the quadrupole thing, which is attractive, took over, and that's the multi-billion-year slowdown in the rate of expansion of the universe. And then we have a multi-billion-year current era, and that's the dipole force that's repulsive. These will come back in terms of galaxy formation scenarios later. Call your attention to spin 4 out there under octupole. Turns out this theory has a notion of conservation of fermion generation in interactions with bosons. And the spin 4 octupole forces are ideally positioned. They do not conserve fermion generation. That would give you neutrino oscillations. And they also seem to have exactly the right strength to explain the astrophysical observations that today's physics interprets as non-zero neutrinos. So we need to add one assumption to get past the first part of this agenda, and I'll do that now. The long-term known ratio of densities in the universe, dark matter to ordinary matter, is a little bit more than 5 to 1. It comes from the CMB observation. And we're going to explain that by assuming that the universe includes 6 isomers of charged particles. And each isomer has approximately its own photon. So that gets you 5 to 1. And then the leftover would most likely be those zero mass, zero charge quarks married up with gluons into hadron-like particles, and you get the rest of that. With this, we can actually go quite a long way. So we need one more thing to get in there, and that is obviously gravity needs to span all 6 isomers. The ordinary matter isomer that we see and the 5 dark matter isomers. So it has a span of 6, and once you drop that into the math, then in fact you get spans for the other forces that we care about here. For example, the dipole repulsive force couples 2 isomers, so actually 3 copies of that. 2 isomers, 2 isomers, 2 isomers, and so forth. I call your attention at the bottom to that 2G68. That is an electromagnetic force, but it also has a span of 2, and as I said, it will be important later. So out of this comes a model for galaxy formation. It's basically kind of a microcosm of how the universe formed, but on a much smaller scale, obviously, and in a much quicker time frame. At the very beginning, the octopole repulsive force is driving stuff away from itself, isomer by isomer. They're all commingled, but they don't really interact very much. And then at some point, stuff is attenuated a bit, and the quadrupole attraction takes over, and you start to get clumps. The clumps are 1 isomer clumps. While that's happening, the dipole force starts to have some significance. And so a clump of ordinary matter is driving away 1 isomer of dark matter. That's very important. That's a repulsive force. And then eventually you get early cores and galaxies based on monopole gravity. So with this, we can explain ratios. There are 2 sets of papers that indicate that the earliest galaxies that we see are essentially all ordinary matter. And so this would be an ordinary matter clump that has yet to accumulate dark matter, but it might. And then there's one paper that has some 4-to-1 ratios for dark matter to ordinary matter. That could be an ordinary matter core that accumulated the 4 isomers that are available of dark matter, or it could be a dark matter core that did not repel ordinary matter that accumulated isomers of dark matter and ordinary matter. So there are 2 ways to get to that particular paper's result. And then finally, if you started with a dark matter core that repels ordinary matter, you can explain the 1 dark matter galaxy that seems to have been studied. And there is just a smattering of ordinary matter stars. So basically, ordinary matter got blown away too early, and there's a little bit left that formed a few stars. There are a few more ratios like this. I'm not incompatible with any of them, either for galaxies or for galaxy clusters. There's one interesting other case here, the Markarian 1216 galaxy, which apparently stopped growing about 6 billion years after the Big Bang. And a possible explanation that comes out of this is that its core actually has 3 isomers in it. Those drove away everything else. And so at some point, this just accumulated all the stuff around it and stopped growing. There are other possibilities too. One more known ratio. There aren't a lot of these. This comes from an entirely different situation. This is the Edges experiment. Any hands? You know what it is? No. Okay. So this came out in the last year. They measured depletion of the cosmic microwave background radiation due to hyperfine transitions or 21-centimeter transitions in hydrogen atoms. They got twice as much as they expected, and it turns out that I offer the explanation that the other half is hydrogen atom isomers, is another isomer of hydrogen atoms, basically, out of the ones we just talked about, not ordinary matter, and so you get 2-to-1 from what theory would have predicted before. So actually, we're in pretty good shape here. We've run this agenda. All green things have been covered. There are some wrinkles off to the side. There's tons of physics that comes out of this that I've not explained. I obviously have not gone into the math, which is based on isotropic pairs of isotropic quantum harmonic oscillators. There is a paper on the web, if you go to that tiny URL, that explains all of this and the other results in a great deal of detail, including the math. And there's also a video at the same length of this talk and a little bit more. Let me inject one more slide just for the fun of it. This is a result that comes out that is testable. The number you see there, first of all, is the ratio of the talon mass to the electron mass. And below it, you see a formula that involves the ratio of the strength of electromagnetism to the strength of gravity. And there's a formula that links those two. If you do the calculation, the two things that really aren't very well known are the gravitational constant and the talon mass. Everything else is known with lots more figures. If you put it all together and run it, you can predict a talon mass that's there. 4 standard deviations, you predict a standard deviation too, it's based on gravitational constant standard deviation. 4 standard deviations of that fit within the current experiment. And so here is a piece of physics that relates possibly the ratio of 2 masses to the ratios of the strengths of 2 forces. There might be something really fundamental beyond this, and there's plenty more beyond it. Time's up. Questions? What do you want to talk about?
Thank you.
Yes?
So since you hit the masses and you said that you'll say why in a dream if they have 0 mass?
That was those octopole spin 4 forces. They do not conserve fermion generation, so we got oscillations. And it turns out that the strength looks like it's for what effects you would get that standard physics interprets. The strength looks like it's the fine structure constant squared times the mass of an electron. If you do that number and multiply by 3, you are square in the middle of the range, almost in the middle, but well within the range of around 1/10 of an electron volt. That is the standard physics estimate for the sum of the 3 masses.
So it's all coming because you're taking multiple.
Yeah, if I'm right, and of course there's lots of conjecture here, but if I'm, there's some experimental evidence on my part, then in fact the problem with traditional physics is that they ran out of things to explain neutrino oscillations or this other effect because gravity wasn't well enough understood, and they pinned it on gravity. It turns out maybe that can push it somewhere else, and it actually makes sense in the theory.
Thank you very much.